Good morning, everyone. I want to welcome you to another multivariate statistic class. Of course, we're starting new chapters today, and of course, what we're starting today um, is actually very critical, but it's not going to be part of the midterm exam. So, what is going to be part of the midterm exam is those that we've done before from I think week 1 and uh week 2. I think something that will finish all the way to yesterday. Okay, so this is a new chapter. Okay, so I want to welcome you to Univariate Bivariate normal distributions. Let me first I'm gonna give an outline that we're gonna walk through. Give me 1 second. So the focus today, like I said, will be on outline number 1 and number 2. We're going to look at univariate normal distribution. I'm going to walk you through bivariate normal distribution. And of course, tomorrow, we're going to focus on the multivariate normal and the sampling distributions. But let me first start from the univariate normal distribution. And how I think I'm going to go by history of normal distribution. We can actually trace the history of normal distribution to 3 fronts. Okay, the first was can be traced so the first can be traced actually to the mover. Okay, the mover in 1733. We can also trace that to Laplace and Gauss. I think Gauss in probably 1809, and the guy in 1783. So the mover actually inherited a problem. You know, the main problem started with Gravesande. You know, Gravesande was actually trying to solve, you know, the probability of, there was a kind of debate about whether there is always going to be equal number of male bats and female bats. Okay, female and male bats. There was an argument about this at the time, but that was very early, between some philosophers about whether we're going to have equal numbers of male bats and equal numbers of female bats. Now, because of that, Grave Sandy, okay, actually collected data on about 11,000 bats, and he observed the 11,000 bats for years. And I'm talking about this guy, okay, William Gravesande. Now, Gravesande actually, collected a sample of 11,429 bats, and the characteristics of interest was, the number of male bats, okay, and he arrived at this. We want to figure out the probability of this. Given that, and definitely you want to solve this problem. Now, Grave Sunday, give me 1 second. Okay, so what I was trying to talk about is that Grave Sunday actually studied 11,429 bats. And of course, it was X is the numbers of May bat. We want to figure out the probability that out of 11,429 baht, the May bat is going to be between this and this. Of course, given that it's 50-50. Okay. Now, uh, using binomial, of course, when the random variable here is discrete, okay, and it's dichotomous in the sense that uh, there are two possible outcomes, male or female. Of course, you're going to use binomial. Has anybody heard about binomial distribution? So the binomial distribution, the probability of that is n combination x p raised to power x 1 minus p raised to power that. That was what they plug in to arrive at this. But if you take a look at this, to solve this, whereas at that time, there was nothing like computer. To solve this, this is complicated, okay? And that was why the mover in 1733 actually used a curve, okay? It approximates binomial distribution with a normal curve, okay? So, that's now led to situation where normal distribution can actually be used to solve binomial problem, but it gave a condition. Okay, so apart from the movers, Gauss gave us the formula for normal distribution. It derived the mean, it derived the CDF, all the statistical properties of normal distribution. Then another person that worked on normal distribution was Laplace. Now, I don't know whether you've heard about central limit theorem. Has anybody heard? Okay, so Laplace was able to tell the world that most of the natural phenomena, okay, given certain condition, they follow normal distribution. Okay, so the distribution follow normal. Okay, so now that you've heard about the history, now let us now look at the formula, like I said, Gauss in 1809 actually derived the formula for normal distribution. And how does the formula look like? This is what you are seeing here. Okay. We call this a probability density function of a normal distribution. Of course, you could have a random variable S that's continuous. If a random variable S is continuous in nature, of course, it could it could follow normal distribution. So this is a normal density, as you can see, and there are two parameters in the normal distribution. Okay, we have the mean, we have the standard deviation. Okay, now a particular random. How do we write that in a short form? If you take a look at what you're seeing here, okay, this is writing that in a short form. When you see that, you know what I mean? That X may be blood pressure. Oh, blood pressure follow normal distribution with a mean mu and a variance sigma squared. Could be whatever variable that follow normal distribution. But if I'm only talking about just one variable at a time, then I will be talking about univariate normal. Does that make sense? Univariate normal. Okay, now, you know what actually makes normal distribution attractive, for use is because of its simplicity. Now, with normal distribution, we can actually standardize. Standardization will lead to will lead to us to the use of z-score. Has anybody heard about z-score? Okay, when you want to figure out probability associated with a normally distributed random variable, instead of you to go by way of rigorous calculus, if you can use the idea of a z-score. Now I present to you our what we call the standard normal distribution. The standard normal distribution occur when the mean is 0 and the variance is 1. That is, the essence of this is to restrict the mean. And imagine you have several set of data. Okay, if I have let me just say 1,000 set of data. What do I mean? Like I have this set of data, one, another set of data, another set of data. Even if each of them follow normal distribution, they are all likely going to have different means. Okay, but how do we, for instance, if I want to compare, maybe I want to compare average in this variable with average in another variable. Okay, I mean, not even if they follow normal distribution, it may be difficult to do. Okay, but if we standardize them, okay, if we standardize this variable, standardize the other variable, then it will make us to have an effective comparison. Okay, restricting them. Okay, that's what we mean. Now, this is the density function of a standard normal distribution. And of course, this is the curve I'm gonna that you are seeing right now. So this is the curve. Okay, it is symmetric in nature. It has a double bed shape. Okay, symmetric in nature, double bed shape, and of course, the center of that. Okay, the center of that is actually 0. You can see here the center is 0. Can you see center? Okay, which is the 0 here? The mean. The mean is the center. Okay, so just take a look at that. Now I'm actually going to move right now. Now, when we have a probability, okay, when we have a probability distribution, what do we want to achieve using probability distribution? We want to find, we're going to use that to figure out the probability associated with a particular random variable. For instance, if a random variable S is income, and income follow normal distribution, and we want to figure out what is the probability of income less than $40,000. That is, I want to figure out the percentage of the household who earn less or equal to $40,000. Okay? If I want to do that, I'm going to use the probability. But because a normal distribution is a random variable that follow normal distribution is continuous, okay, if I want to figure out probability associated with a continuous random variable, then I should be ready to perform an antiderivative. And that's why right now, take a look at this. I want to figure out, you know what this guy is telling me? I actually want to figure out what is the probability, maybe of a blood pressure of my patient to lie between two certain values. Then do I have, what is the PDF for that random variable itself of x? And I'm going to perform an antiderivative. So performing an antiderivative on that, okay, I'm actually going to have f of b minus f of a. Okay, as you can see, where the upper f are the CDF. I want to believe you've learned this in lower course in lower level statistics. Okay, so that is what. But you know what? This is what we need to do. But because of standardization, we're actually going to escape this because standardization facilitates simplicity of probabilistic computation. Okay, now you're going to see as time goes on. Okay, now if you take a look at what I have here, okay, this is a CDF. I want to find the probability of a random variable less or equal to x. That's a CDF. And a CDF is a cumulative probability function lie between 0 and 1. Now, I want to move right now. What I'm displaying right now, when you have any data set, you need to be able to, if you generate this, and that's, this is what you call density plot. If the density plots of your data look like what I'm showing right now, then your data set follow normal distribution. That's exactly what I mean. Now, if you take a look at here, if you take a look at this one, one second. If you take a look at this, that area, okay, if data set follow normal distribution, 68% of the data is expected to lie within. Look at that. That is within one standard deviation. How do I get that? I'm gonna show you what they did for them to be able to get that. And you know what? Uh, if I go this way, okay, that is within two standard deviation. That would be 95%. 95% of the observation is expected to be within two standard deviation. And if I now go all the way, then I'm expecting 99.75% to be within three standard deviation. How did they arrive at that? Okay, how did they arrive at that? I'm going to show you. Okay, so I quickly want to show you this. If I want to find, uh, if I have this guy from mu minus sigma to mu plus sigma, okay, 1 over square root of 2 pi sigma squared exponential raised to the power that s minus mu sigma squared ds. Okay, if you try that, you're actually going to give you 0.68. So if I integrate this is within one standard deviation. Okay, here I want to find the probability of S lie between mu minus sigma, mu plus sigma. Okay, that's why you see that. That will give us 0.68. That was how we say, oh, 68%. Now, if I actually want to go to within two standard deviation, okay, so 1 over square root of 2 pi sigma squared of this x minus mu or this ds would be 0.95. That was how we got that. Okay, within three standard deviation now. Okay, within three standard deviation now. Okay, so integrating that guy, performing an antiderivative. Okay, performing an antiderivative should be 0.9975. Okay, so just take a look at that. So this is for within two standard deviation, within three standard deviation, they have to perform the rigorous calculus to arrive at that. Okay, now I'm actually gonna go back right now. And do you know what we call that? We now call that empirical rule. Okay, that's what empirical rule states. Okay, now I'm gonna move right now. Now I want you to see this. We can have three different data sets. If you take a look at what I'm showing now, okay, this is having data, this is like having mixtures of normal distribution, with different parameters, with different mu and different variance. Okay, if you take a look at this guy here, the red one and this one, they all have the same center. They have the same center, but they have a different standard deviation because they spread out differently. But if you take a look at this one, the green one, of course, the green one have a entirely different center. Okay, so that is what. So when you have different parameters, what do I mean by parameters? When you have different means, we could have, maybe. Okay, let me use this as an example. Blood pressure could follow normal distribution, but the mean of blood pressure is different from height. Maybe height also follow normal distribution. Okay, maybe blood pressure, height, cholesterol level, each of them on their own follow normal distribution, but they have different mean. They have different variances. That is what we're trying to talk about here. And here, okay, this is talking about the CDF. Okay, the CDF, because for every probability distribution function, there's always going to be a cumulative. Okay, now take a look at that. Now, and I want to move right now to affine transformations of normal univariate. For instance, take a look at this. If a variable follow normal distribution like x, please pay attention. Okay, x follow normal distribution. Okay, it has a mean, it has a variance. And we now have a new variable that we want to define, y, and that very y is a function of x. Please pay attention. Okay, that very y is a function of x. Okay, now if x is a random variable and y depend on x, y is also going to be a random variable. If x follow normal distribution and y depend on x, y is also going to follow normal distribution. Please pay attention. Okay. Now, right now, what I'm trying to say right now is if x follow normal distribution as that, okay, and I have a new random variable, okay, I have a new random variable y, and y is depending on s. A and B are constant. In this situation, A and B are not variable. A and B are constant. Then do you know y is also going to follow normal distribution with what? With the mean of A mu and the variance of that. Now, how? Okay, I need you to pay attention. Okay, I need you to pay attention. Okay, so I need you to pay attention. Okay, so like I said, you have x follow normal distribution. This one means normal with the mean of data, and I have a variable y that is equal to ax plus b. Okay, and how do we show that y follow normal? Okay, with a mu. Okay, a mu is the mean. Then the variance is a squared sigma squared. Okay, now I need you to pay attention. Now I'm going to do this. Okay, now here I want to find the mean. It's going to be because here this implies expected value of x equal to mu, variance of s equal to sigma squared. That is what this guy is trying to talk about. Now, right now, I want to find expected value of y, which is going to be expectation of as plus b. Okay, a and b are constant. So here, okay, I'm going to have expected value of as plus b because expectation of a constant is a constant. Expectation will attract a variable s. Now here, what is expected value of s? Mu. So I'm actually having a mu, okay, plus b. So expected value of y. Now, situation here, we are b equal to 0, then my expected value of y is just going to be a mu. Okay. Now, if I want to do the variance of y, which is going to be the variance of ax plus b. Okay. Now, the variance of ax plus b, this is just going to be the variance of as because b is a constant. Okay. Variance of a constant is 0. So here, this is going to be a squared variance of x. Okay, and what is the variance of s? Sigma squared. So I have a squared, sigma squared. Okay, and this is the reason why the variance is that. Is there any question on this? Okay, oh no, those are the kind of things that probably you've done before. Now I'm actually gonna go back. Now with that, you'll be able to understand how to go about if I have this guy now, if S follow, they give you what the mean is. Mean is 1. They give you the variance. They can ask you to determine the distributions of this. Now, let me tell you this. If they wanted to determine the distribution of this, they want you to derive what is the mean, what is the variance. Okay? Now, I'm going to continue, which is what we're doing here. This is the solution now. Okay? If y equal to x plus 3, okay, this is how I'm actually going to do the derivation at the end of the day. The mean is going to be 4, variance is 2. For the other one, the mean is 5, variance is that. So if you try that, that is going to be your. Is there anybody in this class who doesn't understand that? Is there anyone? Okay. Now I'm going to move. I'm going to move right now. Now it's getting tougher. We're actually reaching a stage right now. If I have a normal distributions, how do I figure out uh, the parameters? Because because we don't know those parameters ahead of time. A doctor may not be able to know the average blood pressure of his patient ahead of time. So the question now, if we construct an histogram or we generate a density plot for the data set that we have, the data set on blood pressure. Now the question now, if we know that it followed normal distribution, then how are we going to figure out the parameters? How do we estimate the parameters? So what are the parameters here? The parameters are the mean and the sigma squared. Now to estimate the parameter, okay, we actually want to use the method of maximum likelihood. I need you to pay attention. Now, by the method of maximum likelihood, okay, now if you take a look at this, I know it follow normal distribution, right? This is a normal, right? Then this guy, you know what this guy is telling me? The likelihood function means the joint of the PDF. I want to have that in n time, okay? And they're going to be multiplying each other. Why are they multiplying each other? They are multiplying each other because they are independent. The probability of x1, the joint occurrence of x1, x2 up to xn, okay, then will actually be equal to the joint product, is the product of the respective PDF. Now, if I want to use the method of maximum likelihood, I need to first start from the distribution. I need to know the distribution of the data. And after knowing the distribution of the data, I need to generate the likelihood. And what is just the likelihood? The likelihood is there, is just the product. This sign here, okay, give me 1 second. Okay, this particular sign that you are seeing actually means product. That's a joint PDF. We should mean the likelihood. Now, if I have this guy now, okay, if I have this guy now, okay, you can see the product here. If I want to rewrite this, okay, let me do this. If I want to, I'm going to do it here. If I want to rewrite this, please pay attention. If I want to rewrite this, like for instance, if I don't want to put this, if I don't want to put this one, and I want to write the distribution in joints, this is the constant side. I'm going to raise it to power n. Then here, this is exponential. If I do raise to power n here, there's an s. S is a variable. So what I'm going to do here, okay, I'm actually going to have a summation. Okay, I'm going to have a summation. Okay, now that is what I mean. And after that, okay, what do we want to do? We want to estimate the parameters of the likelihood function, but this is multiplicative. Okay, optimizing a multiplicative function could be complicated. Now, because of that, you know what we do? We introduce a log. We introduce a log. Okay, 1 second. We introduce a log. Okay, we introduce a log to the both side. Why we introduce a log? Okay, for easy optimization, optimizing likelihood function is the same as optimizing the logarithm of the likelihood function, because that would be easy to optimize. Now, after taking the log, this is what we have. After taking the natural log, the way it is now is very easy to differentiate. You got to differentiate with respect to the each parameter. Okay, you differentiate Give me 1 second. Uh, 1 second. What's going on? Mm, let's see. Okay. Okay, so you're going to differentiate each of that with respect to parameter and set to zero. What am I doing here? Differentiating with respect to mu, set to zero. What do I have? It means if I want to have a estimate, the maximum likelihood estimate of the mean will give me the X bar, which is the sample mean. So which means if I have the sample mean is the same. Then what about when I differentiate with respect to sigma? Don't forget there are two parameters. Okay, that's what I'm doing here. Differentiating with respect to sigma set to zero at the end of the day. Okay, that's gonna give me this. Now I need you to pay attention. You remember yesterday I was talking about something over n, right? When you have a covariance over the one that has to do with over n, that is the MLE. Now this is the MLE variance because you see 1 over n, right? But for sample variance, it should be over n minus 1. Do you see the difference? Okay. Now, what have I done so far? I've derived, parametrically, the estimate, okay, of the parameters of the normal distribution using the method of maximum likelihood. The method of maximum likelihood requires that you start from the distribution, and after that, you take you get a likelihood of function of the distribution. Then after that, you take the logarithm of the likelihood function. And after that, you differentiate with respect to the parameter one at a time, set to zero, and solve for that parameter to obtain that. But you know what? How do we do this in R? Now, pay attention now. I have some data. Okay, I have some data. Maybe this data may be on height. This data may be on scores, maybe on anything. And I actually have investigated this data set. I realized that it followed normal. Okay. Now, when it doesn't follow normal, then what we're doing now doesn't make sense. Okay, we are zooming. Okay, so that you are zooming, follow normal, or you have investigated. Maybe you draw the scatter or the histogram. Maybe you generate the histogram, or you draw the density plot, or you do the box plot, and you find out that oh, this is normal. Okay, now the question now: how do I estimate the parameters of a normal distribution? That's exactly what I'm doing. So how do we do this? How do we do this in R? Okay, this is the code in R. This is the coding now. Okay, this way code now will bring you what you want. Now let's take a look at what is going to be in display. So let's take a look at what is going to be in display. Okay, do you see that? It's just going to give you the values. The MLE for the mean and the MLE for the standard deviation. Okay, that's how to do that. Now remove right now. Any question on univariate normal? Any question on univariate normal? We use univariate normal. When you say univariate, we only have one variable and it follow normal distribution. If I want to answer a question that has to do with, figuring out the probability of a random variable, then I'm actually going to use that. But right now, I want to introduce you to bivariate normal. Why is it bivariate? Bivariate in the sense that we are looking at two variables at a time, not one. And the two variables, they are jointly normally distributed. Okay? And let's take a look at that. Bivariate. Now, pay attention. You saw the other time when I give you the formula for the univariate. Now, equation 5 now is a bivariate normal density, and I'm going to explain to you what each of these mean. What we're going to be doing now is will be highly mathematical. If I were you, pay attention. Now, take a look at what you're seeing. You see, there is a mu of s, right? That is the mean of s. Sigma square of s. That is the variance of x. Mean of y. Mean of y. Variance of y. Now you can see the standard deviation is sigma s. Standard deviation for x. Standard deviation for y. Now, what about this guy? What about rho? This guy? That is a correlation. Correlation. Which means, okay, why can't we look at it one at a time? For instance, if I have blood pressure and cholesterol level, okay, why do I want to model them together as a bivariate normal density? Why not separate univariate? Okay, separate, if I look at them separately, if I look at the distribution separately, I'm ignoring the correlation between them. But looking, if you take a look at this now, okay, then I'm putting into consideration there's possibility of them having a correlation, like a relationship. Okay, that's why you see rho. That's it. But you know, there's something I need you to do. If you plug in rho to be zero, if you plug in rho to be zero, you know what you're gonna see? You're gonna see this. If you plug in rho to be zero, f of xy will be equal to this multiplied by that. Where do we have this in statistics? When x and y are independent. Does that make sense? When they are independent, that joint density that I gave you the other time is just going to be 1 over square root of 2 pi sigma squared x exponential raised to power this x minus mu x, okay, over sigma x all squared, then 1 over square root of 2 pi sigma square y exponential raised to power this y minus mu y sigma y all squared. This is what you're going to have. This is what it's going to become. Okay. Now, if you're actually using this, you are assuming that x and y do not have relationship. But with a bivariate, okay, this is going to consider relationship between the variable. Does that make sense? Okay. Now, when relationship exists between two variables and you ignore that, then that's an error in statistics. And that's why we're trying to have, we don't want it to happen. Okay, so this is it. We're just trying to tell you here. We're just trying to tell you here. The mean of x, the mean of y are real numbers. They could be negative, positive, zero. And of course, the standard deviation has to be a positive real numbers. Of course, Of course, then the correlation line between that and that. Now, uh, if you take it then for the marginal, okay, for the, when I talk about marginal, give me 1 second. So when I talk about marginal, that is if I want to look at them one at a time. One at a time is what you are seeing here. X follow that, Y follow normal, that's one at a time. But if I want to look at them jointly, that's what I have. Any question on this? Okay, I want to move right now. What's going on? Okay, so I want to move right now. You know what I'm trying to show right now? For that same joint, like if I come here, if I come to equation 5, and I know the values of some parameter, if the mean of s and mean of y equal to 0, and the variance equal to that, and that equal to that, and I have a rho equal to that, that is the shape that I'm actually going to have. Don't forget, why we have it two-dimensional? We have it two-dimensional because we are considering two variables at a time. Okay, you can see here, this one is a scalar plot, but this is the density plot of each variable. I share, discussed this with you the other time. Okay, Now, what if I have different means? Okay, if I have, for different means, example, if you take a look at this, when the two means are the same, like mean of S and mean of Y are the same, this is where the shape is going to look like. When mean of S and mean of Y are not the same, that's what you're going to have. When they are not the same, that's what you're going to have. Okay, in all of this, you are keeping correlation to be zero. With your correlation, you are keeping correlation to be, to be 0.6 divided by root 2 and the variance. You're keeping all of these constants, but you are varying the means. Okay, that's what you're seeing here. Now here, you are actually varying the correlation. You want to look at the effect of correlation. When the correlation is negative, you can see. When it is zero, when it is positive, can you see that? Why you are keeping all this at constant. Okay, so take a look at that. Now, you are looking at the effect of variances here. Okay, when the standard deviation is 1, okay, when it is that, so take a look at that. Okay, now you are seeing how to find probability with a single variable. How do we find probability with two? For instance, a doctor may want to know uh how many percentage of my patient have a blood pressure, okay, between, give me 1 second. How many percentage of my patient has a blood pressure between A and B? And at the same time, how many percentage of my patient has maybe um, the glucose level to be between A and B? Look at that. I want to look at this simultaneously. That is what we call a joint probability density. Okay, how do I do that? For bivariate, I'm actually going to have two integrals. Can you see two integrals? Why am I having two integrals? I'm having two integrals because I have two variables. Okay. Now, take a look at this. This f of xy will be the bivariate joint density that I show in equation 5. Does that make sense? Okay. So, uh, if I have three variables, that will be three integrals. Four variables, four integrals. That's exactly what I mean. Okay. And we can also find CDF. The other time we're able to find CDF for univariate. Did we find the CDF for bivariate? But you know what? We also have shape, other different shapes that I showed you the other time, plotting y against x, okay, at different values of parameters. Okay. Now, I needed to pay attention. It's getting tough. You remember when we're dealing with univariate the other time, we talk about affine transformation, right? Linear combination, right? If this is what I'm trying to say, if x follow normal with mu and sigma squared, okay, we're able to find the distribution for y, where y is a linear combination of x, right? We did that for univariate, right? Now we now want to do that for bivariate now. Okay, that's what I want to do for bivariate now. Now I needed to pay attention now for bivariate. Okay, now take a look at this. Okay, z is two variables. Okay, if it is two variable, now if you want to follow normal distribution, this is what we're going to write. Because z here is x and y. The mean here is going to be a vector, which is going to be mu x and what? Mu y. It's going to be a vector. Okay? Don't forget that. Then what about this guy? That would be covariance. It's going to be this guy here. Don't forget, where the element in the diagonal will be variances. The first one variance of X, the second one variance of Y, and the other part is the covariance. Okay? Now, if that exists, and I actually want to find a linear combination, please pay attention. If I let A to be this very A, constant, and B to be this. That's another constant. They are not equal to zero. It is not zero element. Okay. Now, how do we define a linear combination? We started again. For bivariate right now, take a look at this. Linear combination. Don't forget, what is my Z? What is my Z equal? My Z is bivariate, X and Y. Okay. My Z is bivariate, X and Y. My A is a matrix of constants. My B is a matrix of constants. Okay. Now, if W equal to that, then we can find the distribution of W. The distribution of W is going to be A mu plus B. You remember the other time, it was a single A mu plus B, right? Now, this time around, it's going to be this. Please pay attention. Now, this is a distribution when it comes to that. Now, I'm going to move right now. Do we know that from a joint distribution, we can figure out conditional distribution? If you want to go by probability, you remember probability rule. Okay, you remember probability rule. What is the probability of A given B? Is probability of A intersection B. You remember that? So the same thing if I have f of x given y. Okay, f of x given y. The doctor wants to know what is, if I know the blood pressure of my patient, can I actually, or if I know the temperature of my patient, can I actually determine what the BP is going to be? So here, I will actually need joint divided by the marginal. Okay, the joint divided by marginal. Now, I need you to pay attention. There's a lot of mathematical work here. Okay, now, f of y given s equal to that. Okay, and f of s is the marginal. This is the joint. Now, pay attention. We've been able to derive this. Okay, we've been able to derive this. You know, what is y given s? We want to know the distribution of y given s. Okay, if the distribution of the y given s, we follow normal distribution with the mean and the variance. How am I going to find the mean? This is the mean. That's a conditional mean. This is a conditional variance. But let me tell you this. When correlation is zero, what happened? When correlation is zero, what happened? Conditional variance is going to be the same as the variance of y. Can you see that? So that's what I'm saying. You have a conditional mean, we have a conditional variance. Okay? Conditional mean and conditional variance. Okay, so these are formula for that. Okay? Now, I needed to pay attention. How do we derive it? This is the derivation. This is the proof. Okay? This is the proof. Okay? That is the derivation. Okay? Now, situation where they are independent, you're only going to have a product, right? When they're independent, you're only going to have a product. Now, this is for the conditional probability. Let me see if I can quickly go to, I can have an example here. Now, let's have this example. I think this time is very fast, so it's 12:03 here. A statistics class take 2 exams. Exam 1 is X, exam 2 is Y, where the scores follow a bivariate normal distribution with parameter. Now you're giving the mean of X, the mean of Y, the standard deviation for the two, and the correlation. Can you see that? You're giving all of that. Now the question say, Suppose we select a student at random. What is the probability that the student score over 75 on exam 2? Because that question is only focusing on exam 2, you will use a marginal. Okay? Now, if I want to solve for exam, if I want to solve for that, you see that? For y, I know the mean, they've given you that. I want to find the probability that y greater than 75. You remember what we did in lower statistics? Y greater, look at that, over 75 means greater than 75. And I'm going to use I'm going to use standardization. I told you the other time, I don't need to go for rigorous calculus. Then I will that probability is going to be there. You can see here, I'm only focusing on y because it says exam 2. Don't forget, exam 2 is y, exam 1 is x. But look at question 2. Look at question B. The student score over 75 on exam 2, given that the student score 80 on exam 1. That's a conditional one. A conditional one, I need a conditional mean and conditional standard deviation. Now, take a look at that. You remember the other time when I was writing the formula for conditional mean and for conditional variance? You just plug it down in. You derive that as conditional mean, conditional variance. Then you come here to use it. Can you see that? You're still going to standardize. You're going to use the idea of a z-score. Can you see that? Using the idea of a z-score. Can you see that? So what am I using here? The mean that I computed using the formula. Can you see that? And the variance that I computed using the formula. Okay, this is square root of 144, 12. So I go to table, I got that. Can you see that? That's super easy. Now, there are other questions. The other question here. The sum of his exam 1 and 2 is over 150. Sum of exam 1 and exam 2. That is probability of x plus y. For probability of x plus y, you need the mean and the variance too. Look at that. X plus y. What is the mean? You add up the mean. What is the variance? You add up the variance, then 2 multiplied by that. You plug that in. That will give you 130, 505. Use it again. Can you see that? That is the probability of the sum greater than 150. What is the last one? The last one said, what is the probability of 5x minus 4y greater than 150? That would be easy. I need the mean of this guy. I need the variance. Now, look at that. Can you see what I'm doing? Oh, wait a minute. Oh, that one is for the difference. Okay, can you see that? And this is that. You see that? I got the mean, I got the variance, then I use it. Can you see that? And if you want to do that in R, I think I provided an R code for all the questions. But I allow you to use an R code. Very easy using an R code for all the questions. This is not going to be on exam 1 or the midterm that we want to do on Friday. Like I said, what we started today. Any question before I go on this? I have time to explain. Any question on these ones? I need somebody to ask question. If you don't understand any of this, if you don't understand how to go about this, is there anyone doesn't understand that? Everything is okay, right? You sure? Okay. Make sure you all stay safe. That's all what I have for you for today. Make sure you all stay safe. Have a lovely day. See you tomorrow. Bye for now.